Hi class, how are you today? Well, I took a sample of responses, and from that data, I can infer that that must be great. The learning target for today is to be able to describe sampling distribution terms and construct a relative frequency distribution. For the scale, you're a 3 if you can describe sampling distribution terms and construct a relative frequency distribution. You're a 2 if you can describe sampling distribution terms or construct a relative frequency distribution. You're a 1 if you can describe some sampling distribution terms. And you're a 0 if you cannot describe sampling distribution terms or construct a relative frequency distribution. Let's get started. Section 6.4, Sampling Distributions. Focus points for this lesson: review such commonly used terms as random sample, relative frequency, parameter, statistic, and sampling distribution. And from raw data, construct a relative frequency distribution for x-bar values and compare the result to a theoretical sampling distribution. A lot of this is going to be review, and it is actually a pretty quick section on top of the fact that a lot of it's review. But a lot of the stuff we haven't touched since Chapter 1 or Chapter 2, so we want to make sure that you know what it is going forward because it will be really important. Let us begin with some common statistical terms. Most of these have been discussed before, but this is a good time to review them. From a statistical point of view, a population can be thought of as a complete set of measurements or counts, either existing or conceptual. So population is everything, all of the measurements or counts or people, whatever, that exist in a specific group. A sample is a subset of measurements from the population. For our purposes, the most important samples are random samples. So samples are a part of the population, not all of the population. When we compute a descriptive measure, such as an average, it makes a difference whether it was computed from a population or from a sample. A statistic is a numerical descriptive measure of a sample. A parameter is a numerical descriptive measure of a population. So if we say statistic, we're dealing with a sample. If we say parameter, we're dealing with a population. That's the only difference between the two. Some commonly used statistics and corresponding parameters. So if we're dealing with a mean, for a statistic it's x-bar, for a parameter it's mu. Variance for a statistic is s squared, for a parameter is sigma squared. For standard deviation, for a statistic it's s, for a parameter it's sigma. Notice that a variance in both cases is just the standard deviation squared. And for a proportion, which we haven't gotten into yet, but we will be soon, it's p hat, or for a parameter, it's p. So if it's got the hat on it, it's a statistic. If it doesn't, it's a parameter. Often we do not have access to all the measurements of an entire population because of constraints on time, money, or effort. So we must use measurements from a sample instead. In such cases, we will use a statistic such as x-bar, s, or p hat to make inferences about a corresponding population parameter. And those examples are mu, sigma, p. The principal types of inferences we will make are the following. Estimation. In this type of inference, we estimate the value of a population parameter. Testing. In this type of inference, we formulate a decision about the value of a population parameter. And regression. In this type of inference, we make predictions or forecasts about the value of a statistical variable. To evaluate the reliability of our inferences, we will need to know the probability distribution for the statistic we are using. Such a probability distribution is called a sampling distribution. Perhaps example 11 will clarify this discussion. A sampling distribution is a probability distribution of a sample statistic based on all possible simple random samples of the same size from the same population. Pinedale, Wisconsin is a rural community with a children's fishing pond. Posted rules state that all fish under 6 inches must be returned to the pond. Only children under 12 years old may fish, and a limit of 5 fish may be kept per day. Susan is a college student who was hired by the community last summer to make sure the rules were obeyed and to see that the children were safe from accidents. The pond contains only rainbow trout and has been well stocked for many years. Each child has no difficulty catching his or her limit of 5 trout. As a project for her biometrics class, Susan kept a record of the lengths, to the nearest inch, of all trout caught last summer. Hundreds of children visited the pond and caught their limit of 5 trout, so Susan has a lot of data. To make the next table, Susan selected 100 children at random and listed the lengths of each of the 5 trout caught by a child in the sample. So here is half of the table, and here's the other half. You can also find it on page 316 in your book. But in these, for each sample, there are 5 lengths for each fish, and then the sample for each child of their 5 fish. So the sample mean of each. Then, for each child, she listed the mean length of the 5 trout that the child caught, which I just showed you. Now let us turn our attention to the following question. What is the average length of a trout from the Pinedale Children's Pond last summer? We can get an idea of the average length by looking at the far right column of table 6.9, but just looking at 100 of the ETS values doesn't tell us much. Let's organize our ETS-bar values to a frequency table. We used a class width of 0.38 to make this table. So if you remember back from chapter 2 of frequency tables, so we have our lower and upper limits, our frequency of how many fall in the class limits, and the relative frequency, so pretty much the frequency divided by 100, because there were 100 samples taken. So frequency divided by n, the number of samples. In this case is 100. Note, earlier it had been dictated a class width of 0.4, however this choice results in the 10th class being beyond the data. Consequently, we shortened the class width slightly and also started the first class with a value slightly smaller than the smallest data value. The far right column of table 6.10 contains relative frequencies, f divided by 100. We know that relative frequencies may be thought of as probabilities, so we effectively have a probability distribution. Because ETS-bar represents the mean length of a trout, based on samples of 5 trout caught by each child, we estimate the probability of ETS-bar falling into each class by using the relative frequencies. So here is a relative frequency or probability distribution of the ETS-bar values. So, looking pretty normal. So, starts out low, gets big in the middle, and then back down. The bars represent our estimated probabilities of ETS-bar values based on the data of table 6.9. That was the really big one. The bell-shaped curve represents the theoretical probability distribution that would be obtained if the number of children, i.e. number of ETS-bar values, were much larger. Figure 632, the last one with the normal and the figure, the frequency distribution, represents a probability sampling distribution for the sample mean x-bar of trout lengths based on random samples of size 5. We see that the distribution is mound-shaped and even somewhat bell-shaped. Irregularities are due to the small number of samples used, only 100 sample means, and the rather small sample size, 5 trout per child. These irregularities would become less obvious and even disappear if the sample of children became much larger, if we used a larger number of classes in figure 632, and if the number of trout in each sample became larger. In fact, the curve would eventually become a perfect bell-shaped curve. We will discuss this probability at some length in the next section, which introduces the central limit theorem. Alright, now time for the sponge. Number 1, explain the difference between a population and a random sample, give an example that identifies both. And number 2, explain the difference between a statistic and a parameter, and give an example of each. That's it for the lesson. Once again, please make sure to take notes on the entire lesson. Take a picture of everything, submit it all to Google Classroom, and have a good night.